In this video, we will discuss the basics about the sampling theorem. So what is sampling theorem? It is a process of converting the continuous signal into discrete signal. You can say that a continuous time signal can be completely represented in its sample and recovered back if the sampling frequency is greater than or equal to twice of the highest frequency component of the message signal, that is FFM. Mathematically, you can write the sampling theorem using this equation that f of s should be greater than or equal to 2 times f of m. So like sampling is usually required in order to convert the analog signal or the continuous signal into the discrete time signal. And for example, if you are given an analog or continuous signal using this sine pulse, on the x-axis is the time and y-axis is x of t, and you have to convert that signal into discrete time domain signal, so then you have to multiply that signal with the pulse train. Like you can represent the pulse train using this signal, where you can see that Ts is basically the time duration between the samples. Like you can represent the Ts, that is the time duration between two samples. So that is known as Ts, and you can calculate what is f of s. So f of s is equals to 1 divided by Ts. So if you multiply the pulse train with this continuous signal, you will end up with the discrete time signal. There x of n multiplied by Ts will give you the value of the sample at a particular time. For example, if a signal is given x of t is equals to sine 2 pi t plus sine 3 pi t plus sine 4 pi t, and you are asked to calculate what is the frequencies or the number of frequencies present in this signal, or you can say what is the highest frequency component in this signal. So simply you can calculate the frequency component in this signal. Like you can say that, okay, you know that if these are three signal, like sine 2 pi t is one signal, sine 3 pi t is another, and the sine 4 pi t is another component in one signal. So you can say that, okay, so this is omega 1 t. Like you can represent sine 2 pi t in a general format like sine omega t. So it means that omega is the frequency, like the angular frequency. So you can write here omega 1 is basically equals to 2 pi, and we know the general formula of omega, so that is 2 pi f. So you can equate them together. Like here you can write omega 1 is equals to 2 pi, and in place of omega 1 you can write 2 pi f1, so that is equals to 2 pi. So 2 pi will be cancelled with that 2 pi, the remaining is f of 1. So similarly, if you see this component sine 3 pi t, you can say omega 2 is equals to 3 pi, and we use the same formula, omega is 2 pi f, so it is 2, so we can write 2 pi f2. So we can equate them again. So 2 pi f2 is equals to 3 pi, so we can calculate f of 2, so that is f of 2 is equals to 1.5. And now we can calculate for the third component, so omega 3, so which is equals to 4 pi, so 2 pi f3 which is equals to 4 pi, or you can say f3 is equals to 2. So this is f3 is equals to 2, so this is f2 that is equals to 1.5, and this one f1 which is equals to 1. So you can calculate f of m, which is the maximum of these three frequency, like max of f1 comma f2 comma f3, so max is 2. So you can say that f of m is equals to 2. So to completely recover that signal, fs should be bigger than 2 hertz, like 2 times bigger than 2 hertz, or you can say that it should be 4 hertz. So the at least case of sampling theorem, so that is known as Nyquist rate, you can say f of s, so that is equals to 2 multiplied by f of m, and this is known as a Nyquist rate. In case f of s is less or does not follow the sampling theorem, then the recovery of the message becomes difficult and you will end up with distorted waveform. We can solve few problems related to the sampling theorem. For example, sampling frequency of that signal we need to calculate. Like what should be the sampling frequency if we want to recover this signal back, because on the transmitting side you have to convert that signal into the discrete time signal, and on the receiving side you want to convert or you want to recover it exactly the same. So what sampling frequency should be? So we know the criteria for the sampling frequency, that the sampling frequency should be at least equals to 2 times f of m. So we don't know f of m, we have to calculate what is the f of m first. So that signal is given. So in this signal we know what is W1. So W1 is equals to 100 pi t, and we know the general formula for the W, that is 2 pi f. So we can write 2 pi f1 is equals to 100 pi, where we can calculate what is f1, 2 pi on the other side, the pi will be cancelled with that pi, and 50 times 2, that is 100. So f1 is 50 hertz. Similarly, we can calculate W2 from this cos 200 pi t. We know that is W2 is equals to 200 pi, and we again use the same formula, 2 pi f2 is equals to 200 pi, and where f2 will be equals to 100 hertz. And now we can say what is fm using this formula. F of m is equals to max of f of 1 comma f of 2. So we know maximum from this is 100 hertz. So fm is 100 hertz. So we know the sampling theorem, f of s should be greater than or equals to 2 times f of m. So in that case, if we use f of m is 100 hertz, so the sampling frequency should be at least 200 hertz. There is another example, like if a signal having a frequency component of 0 to 10 hertz is sampled at 10 hertz, then you need to see what is the criteria. Like the Nyquist criteria says that f of s should be greater than or equals to 2 times f of m. But in this case, we know the sampling frequency f of s is 10 hertz. But according to the given components 0 to 10 hertz, your maximum frequency or f of m is 10 hertz as well. So it means that your f of s, that according to the Nyquist theorem, it should be 2 times greater than f of m. But from these results we can say that f of s is equals to f of m. So it means that this does not satisfy the Nyquist criteria. So this shows that f of s is much less than 2 times f of m. So that is why in such case the resultant signal is highly aliased, and the graph of the aliased signal is given like this. Like you can see that the signal is like overlapping each other. That is why this is the overlapping region is known as aliasing. There is another example, that if you are given a spectrum of the signal where the least frequency is 12 hertz and the last frequency is 20 hertz, and you are asked to calculate what is the sampling frequency of the signal. So in order to calculate the sampling frequency of the signal, we can use the Nyquist theorem. So where f of s should be greater than or equals to 2 times f of m, and we don't know what is f of m, we can calculate from this spectrum. So f of m is basically equals to max of these two frequency, 12 hertz and 20 hertz. So max of these two frequency is 20 hertz. So we can use that in place of f of m. So and then we can say that f of s is equals to 2 times f of m, and f of m is 20 hertz, so 2 times into 20 hertz, so which is equals to 40 hertz. So the sampling frequency should be equals to 40 hertz. We have another question where we basically need to calculate what is the sampling frequency of the given signal. So this is a homework for you. Like you need to calculate the sampling frequency for this given signal, and let me know what is your answer.